The fundamental theorem of line integrals. Let C be a smooth curve joining A to B, and let C be parameterized by the vector function r of t. Let F be differentiable with a continuous gradient field, big F equals del F, on a domain D containing the path C. Then, the path integral of F along C is the difference between f of b and f of a. The fundamental theorem of line integrals says that no matter what the path connecting a and b are, we'll get the same value if we're dealing with a gradient field. And that value will be the difference between f of b and f of a, evaluating the potential function at the endpoints. Now, assuredly, this means that if I have a gradient field, then I have a path-independent integral and a conservative field. Later on, we'll learn that that result's just a little stronger, that all my gradient fields are conservative, and also all the conservative fields are gradient fields, but that's looking just a little far ahead. Right now, what I'd like to talk about is the proof of the fundamental theorem of line integrals. What this really does for us is if we have this situation where we have a gradient field, evaluating one of these path integrals is, well, a lot easier now. So the idea of the proof actually starts with the derivative along a path, which is a formula we saw a while ago in the course. And that formula was this. So let's say f is a vector, f is a function. Then we saw that the derivative of f of r of t was del f evaluated at r of t dot dr dt, or r prime of t. That's that result we saw, and it's really a chain rule that if you have t, you plug that value t into functions that give you x and y, or maybe even z or w, or however many variables f is on, and then you plug all of those variables in to get f. Well, then the chain rule, using this dependency diagram, and I'm just doing this for two variables, but you can imagine all the other rows I get, df dt along this path, exactly what I have here, right? The derivative of f with respect to t along that path is the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. And if there were more variables, I just have more of these dependency branches, and this is a dot product. Partial of f with respect to x, comma partial of f with respect to y, dot dx dt dy dt. And what I have here is del f dot r prime of t. And so that relationship is going to come up here in the proof for the fundamental theorem of line integrals. So what we have is a path integral of f dot dr, but f is actually del f for some potential function. And I'm going to go on and write it down as big F of t dot dr dt dt. And instead of saying along C, now I know I could imagine going from some parameterization A to B. All right, and so what I'm really doing here is just taking my line integral and thinking about it in that computational way, and going and saying, hey, big F, that's not just a vector field, that was a gradient field. All right, well, now I recognize this part, right? That's what we derived here, right? Del f dot dr dt. So I can rewrite that as d dt of f of r of t dt. And so this is a definite integral of a derivative dt. Well, the fundamental theorem of calculus says, well, that's just f of r of t evaluated from a to b. Well, when I plug b into my path, it gives me a point, the point I end at, or f of b. When I plug a into the path, well, that's pointing at the point I started at, and that's f of a. And so there's a very quick justification of the fundamental theorem of line integrals. And I thought we'd end this lesson by doing an example. So here I have what I hope is a familiar vector function. We used this as an example in the last video I made. So big F was this vector function, and we actually found its potential function. If you haven't watched that video, you can pause this and go back and watch this, the video before on the playlist. If you just wanted to pause the video and make sure this really is the potential function for this, right? Make sure that when you take the gradient of this, you get that back, that would be fine too. Now we're asked to take a path integral along a helical path connecting 0, 0 to 1, 1 pi, and we don't know a lot about that path. It's some helix that connects them. But because this big F is a gradient field, I know the kind of path doesn't actually matter. The only thing that matters is where I start and where I stop. And all I have to do is evaluate my potential function at those 2 points. So I'd have f of 1, 1 pi minus f of 0, 0, 0. Well, f of 1, 1 pi. Well, that's 1 times 1 is 1, and the sine of pi is 0. And then f of 0, well, let's see, it's going to be 0, and well, I get 0. And it was a fairly simple process. I guess the challenging part would be is that if someone gave me this vector field, I'd have to recognize that it was a gradient field. Otherwise, I might be trying to parameterize the path, which I really don't have enough information to do just based on it being called helical, and I might not think to use the fundamental theorem of line integrals. So this is something we're going to have to talk about in future videos, how I knew this would be a gradient field, and therefore I could use the fundamental theorem of the line integral.